Welcome to the last little video for chapter 2. Again, in this chapter, we're looking at visual displays of quantitative and qualitative data. And so this 2.3 is, they add on about 5 or 6 different types of graphs in the book, but I'm going to cover 3 or 4 that I think are important and useful. And the first one that we're going to look at is a stem and leaf graph. A stem and leaf graph, or a stem plot, sometimes it's called, comes from the field of exploratory data analysis, and it's a good choice when the data sets are small and usually discrete data, but sometimes decimal data will work just fine as well. And I'm going to show you what one looks like here. So this is from our book. This is data on outpatient testing on the number of cardiograms performed each day for 20 days. And so this is what it looks like. So you're going to have a digit, the first digit of your numbers on this, what they're going to call the stem. And then the second digit is going to be the leaf. And so in this case, the numbers you could see were single digits. So 2 cardiograms done in a day, up to, I can see that there's like 57 cardiograms done in a day. And so, so they've chosen to do the tens digit as the stem and the ones digit as the leaf. Okay, so let's go back to explain how it's done here in the notes. So to create one, you're going to divide each observation of data into a stem and a leaf. The leaf consists of a final single significant digit. For example, the number 23 has stem 2 and leaf 3. The number 432 has stem 43 and leaf 2. Likewise, the number 5,432 has stem 543 and the leaf is 2. So the leaf is always the single digit to the right. The decimal 9.3 has stem 9 and leaf 3. So, and then you write the stems in a vertical line from smallest to largest. You draw a vertical line to the right of the stems, and then write the leaves in increasing order next to the corresponding stem. So preferably in increasing order, they can be mixed up, but to make it look nice, do the leaves in increasing order. So we're going to create one. You can look through the book for lots of great examples as well. For Susan Dean's spring pre-calculus course, scores for the first exam were as follows. And I have them listed smallest to largest, so that benefits you. So what I did was, you should always have a key so that the reader knows what is your stem and what is your leaf. So the tens are our stem and the leaves are the ones. And the smallest data value we have is 33, so I started with 3. Now you could have started with 0, 1, and 2, but there's not a need because there weren't any data values in those numbers. And then you can see the next number is 42, so that goes with 42. And there are 2 data values that are 49. See, 49 and 49. So you have 49, 49. So the nice thing about a stem and leaf is you can see the raw data because by every leaf is an actual data point. And you can see that the largest data value on the score on the pre-calculus course was 100. Now, if there was a stem that had no data observations, you still need to list that stem if it falls in between your smallest and largest, because the reader needs to know that there was a gap in the data. That's important. So something we can gather from this stem plot is that most scores fell in the 60s. You can see that here. Some in the 70s and 80s. And then again, there's quite a few in the 90s. 8 out of the 31 scores are approximately 26% of them were in the 90s or 100. So students scored fairly well. Example 2 says, for the Park City basketball team, scores for the last 30 games were as follows. Again, I was nice and presented them smallest to largest for you. They won't always come that way. I also gave you a key. So the key says the tens are going to be our stem and the ones are going to be our leaf. And I started with the 30s. So I'm choosing to go, it looks like I've got some numbers in the 30s, 40s, 50s, and 60s. So I have 4 different stems I'm going to use. So I'm going to use the stem of 3, 4, 5, and 6. And remember, every data point should have a leaf. And so I have 2 32s, and because they go in order, it's kind of easy for me to keep them in numerical order. A 33, a 34, and a 38. So those are all my 30s. And then I have a 40, 2 42s, 43, a 44, a 46, 2 47s, 3 48s, and a 49. I try to cross them off as I go to keep them straight. I really am particular about crossing them off when they're not in numerical order, but since these are, I can easily go back and make sure I have used them all. So there are 2 50s, a 51. There's 1, 2, 3 52. So I need 1, 2, 3 2s. There's a 53 and a 54, a 56, a 57, a 57, and then a 60 and a 61. And then I wrote, what is an observation you can take from the stem and leaf plot? And then we looked at shape in one of our previous sections. And so on this one, I would say that the shape looks symmetric. That's one observation I could take here, which tells me that most of my data appears to be centered in the middle. There aren't a bunch of data points this way or this way, which those would be considered extreme or unusual. And that's what I gave you down here. So just talking about an outlier. An outlier is an observation of data that does not fit the rest of the data. It is sometimes also called an extreme values. So that would have been maybe had one of the games where they scored in the 80s, that would be unusual. Or one game where they scored very low, maybe only in the 10s or 20s. So the next one is the distances in miles from the homes of off-campus statistics students to the college. Create a stem and leaf plot. So it looks like, and again, I gave them to you in numerical order. So it looks like somebody lives a half mile away, 7/10 of a mile, all the way up to somebody who lives 8 miles away. So in this case, my key, I'm going to say 0.5. My key means 0 is going to be my stem and 5 is going to be my leaf. So I've got some that are only a half mile away, all the way up through in the 1 to 2 miles away, 2 miles away, 3, 4, 5, 6, 7, 8. And now you might be wondering already, well, there are none in the 6 and 7 miles away, and that's okay. I have one person that's 8 miles away. I'm going to cross that off. And then they jump down to the 5s. There's a 5.2, a 5.5, a 5.7, a 5.8. And so I still have to have a placeholder visually for the 6 and 7 so that I can see the big picture of what's going on with the data. Go ahead and fill this out with me. Quite a few students that live within about 1 mile to 2 miles away from the school. A couple in the 3 mile range and a couple in the 4 mile range as well. But one thing I really noticed is the outlier. So that student that lives 8 miles away doesn't seem to be a typical student in this class, in this sample here of the off-campus students. The side-by-side stem and leaf plot is a nice way to compare two data sets that maybe have something similar or different that that makes them different, that you want to compare them. So we're going to look at an example here. The table shows the number of wins and losses the Detroit Pistons have had in the last 20 seasons. And so I'm going to do the wins on the left and the losses on the right. Now, they should be opposite of each other, right? If you have 100 games in a season, you're either going to have the majority in wins and fewer in losses, or fewer wins and majority of losses. But it's just a great example for us to be able to compare the two. Now, they're great. Double stem and leaf plots are great if you're doing like on-campus students versus off-campus students, or your morning statistics class versus your afternoon statistics class, or two genders, male versus female, something like that. Okay. So in the wins, it looks like our lowest win was 20 and our lowest loss was 18. So I'm going to have in the teens, the 20s, the 30s, 40s, 50s, 60s. I don't know that there were any in the 70s. And we're going to go from smallest to largest from inside out. So on the losses, my lowest here is an 18, I believe. And then there are no teens on the wins. And so I'm just going to kind of, the ones with the 0 I know started the inside, so I can mark that on the wins. And then there's a 30 there. I'm just picking some that are easy to start with, the 0 on the 20. And then on the losses, we have a 50. Okay, and then we could do on the losses, we've got 32, 32. There are no 31s, so we can start with 32, 32. 23 looks like the lowest in the 20s. So this 23, and there's a couple of 28s and a 29. Those are all the 20s on the losses. And then on the 30s, we have a 38 as well. And then we go to the 40s, the lowest one is a 41. There's 2 of those. And then there's 43. And then another 43 here. And a 45 and a 46. And in the 50s, there's 2 52s, a 53, 53, and 55. And then on the wins, 41. It looks like we have 25 to 29, 32, 37, 39. Oh, I missed the 23, so I'm going to go slip that in here. 44. So it looks like I have everything over here crossed off, and I'm going to go over here. Oh, there's a 39, another 39 I missed. Oh, and a 27. Put it in there. In the 50s, we got a 53. 2 54s. 59, and then a 64 is the largest number of wins. It just gives you a good picture of double stem and leaf plot. A line graph is another graph that's used sometimes. It's similar to histogram, it's just lines instead of bars. It's useful for specific data values in a line graph. In particular, line graph shows in the example below, the x-axis consists of data values and the y-axis consists of frequency points. In a survey, 40 mothers were asked how many times per week a teenager must be reminded to do his or her chores. The results are shown in the table below. So if you have children at home and the average number of times they need to be reminded, is it 3? Because it looks like that is the kind of the peak number where the majority of children, teenagers need to be reminded 3 times. 14 of them said 3 times. And so you can see that in the graph that I created for you. I'm not going to create any of these. Just going to show them to you. In this one, a survey of 40 people were asked how many times per year they had their car in the shop for repairs. The results are shown in the table below. And this one is shown. You can see here in Google Sheets, it's very similar to Excel. I put in the table right here in the top left, the number of times in the shop. And then you can just grab, actually, if you grab the titles even, I didn't do that, but if you grab the titles and just hit insert and go to chart, it will bring up and see how it even gave me a title here. And then it put my x-axis, the number of times in the shop, and the frequency here on the vertical axis. So it knows what's going to fit your data well. And then this leads into the bar graph, because bar graphs are another great way to show quantitative, but also really well for qualitative data. And this is still quantitative data, quantitative discrete number of times in the shop, but you can see that the bar graph is a nice way. I kind of like the bar graph actually even better here, just because I'm a visual person and the bars are big and it kind of sticks out to me. So let's go to the next example in our notes. It's also with bar graphs. And this is by the end of 2011, so long ago, 13 years ago, Facebook had over 146 million users in the US. The table below shows 3 age groups, number of users in each age group, and the proportion or percentage of users in each age group. And so I constructed a bar graph in these age groups of the proportion is what I did here. And actually, I could have done a histogram because this is numerical data. And then they would have been touching, because that's what a histogram does. And I'm going to skip that one for now. Time series plots, another more like a line graph. Time series plots are unique because they are based on time, so they have to go in chronological order. So to construct a time series graph, we must look at both pieces of our paired data set. We start with the standard Cartesian coordinate system. So the horizontal axis is used to plot the date or time in increments, and the vertical axis is used to plot the values of the variable that we're measuring. So by doing this, we make each point on the graph correspond to a date and a measured quantity. The points on the graph are typically connected by straight lines in the order in which they occur. This data here is from the Consumer Price Index for 10 years. So what is the annual Consumer Price Index here? So all the way from January of 2003, so all 12 months, all the way through December of 2012. So quite a bit of data. And this is what it looks like in a time series plot. So the youngest, or the oldest, I should say, year all the way to the most current year. So if you go to Yahoo Finance and look up stock prices, where you can invest in companies and such as that, they're going to use a lot of these types of time series plots. Example 10 is another example of a time series plot. It is on carbon dioxide emissions in the UK, the Ukraine, and the United States. And 2003, it started comparing up to 2009. And obviously, we're a much larger country than either of those. So obviously, we're going to have a higher CO2 emissions. I would be interested in seeing the US compared to China. I would be interested in seeing that, because I would guess that they're very close, if not a higher usage of products that create CO2 emissions. So here we are with this very faint line up here, the US, and then they're down here. Also making sure, just talking about some bad displays of data, we have done that. Making sure that they start at 0, because if they don't start at 0, then the graph is distorted. So that's an important thing to look at on graphs. And just wanted to touch base on pie charts. We didn't go over any pie charts in this course. We have they are used quite a bit. Pie charts are a good use of any type of data, mainly qualitative data is good, but the key is you have to have 100% of the data that you're looking at, because that's what a circle or pie chart is based on, is 100%. So all of the pieces will add up to 100%. And then I just give another example of a dual bar graph here. And then reminding you, quantitative data, we said histogram is probably the best. And then we're going to be looking at a graph called a normal distribution for that symmetric data later down the road. And just wanted to take note of two things to be concerned about: percentages that add to more or less than 100%. So that's always, if you see a pie graph or a bar graph, especially a bar graph, this mistake is made quite a bit, where the bars will add to be more than 100%, then something is not right about their data. Also, sometimes they'll have an other or unknown or missing data. That's important to look for, because that's a clue that it's not a good display of data. 3D charts are not good either. I would definitely be leery of any 3D charts or graphs that you might see. So that concludes chapter 2 on visual displays of data. And we're going to move into chapter 3, where we're going to start looking at numerical ways to describe our data. Catch me back for another video.